Scientists thought Proxima B could be our backup planet. It's located in the habitable zone, just 4.2 light-years away, practically next door in cosmic terms. But new data reveals something far darker. This isn't a second Earth. It's a radiation-blasted hellscape locked in place, with one side eternally scorched and the other frozen solid. Massive stellar flares rip across its surface with energy that would obliterate any atmosphere we recognize. The planet we thought could save us might actually be one of the most hostile places we've ever found. And here's the disturbing part. If our nearest neighbor is this deadly, what does that say about the rest of the galaxy? The search for another Earth began long before we had the technology to see beyond our own solar system. But it was on a quiet Wednesday in August 2016 that the abstract dream coalesced into a tangible reality. The European Southern Observatory in Garching, Germany, became the epicenter of a seismic shift in astronomy when scientists announced the detection of a world orbiting Proxima Centauri. This was not just another entry in the growing catalogue of exoplanets, which had already numbered in the thousands. This was different because of its proximity. At just over 4 light-years away, the host star is our nearest stellar neighbor, a red dwarf that has silently accompanied the Alpha Centauri system through the galactic void. The discovery of Proxima B marked the end of a specific kind of loneliness for humanity. The realization that the very nearest star to our own sun harbored a planet with a mass similar to Earth. The detection method used to find this world was a triumph of precision and patience known as the Pale Red Dot campaign. Unlike the transit method, which relies on a planet passing directly in front of its star and dimming its light, the discovery of Proxima B relied on the radial velocity method. Astronomers spent years monitoring the subtle movements of Proxima Centauri, looking for the telltale wobble caused by the gravitational tug of an orbiting body. As a planet circles a star, gravity is a two-way street, and the planet pulls back, causing the star to move in a small circle. By analyzing the light spectrum of the star, scientists could see the wavelengths compressing as the star moved toward Earth and stretching as it moved away. A Doppler shift that revealed the presence of a companion. The data was unequivocal, showing a periodic wobble every 11 days, indicating a planet orbiting at a blisteringly close distance, yet one that sparked immediate hope for habitability. This excitement was rooted in the specific nature of the host star. Proxima Centauri is a red dwarf, a Class M star, drastically different from our own G-type yellow sun. It is much smaller, with only about 12% of the sun's mass, and significantly cooler, emitting a dim, ruddy glow that is invisible to the naked eye from Earth. Because the star is so cool, its heat does not reach very far into space. This seemingly inhospitable trait is exactly what made the orbit of Proxima B so intriguing. The planet circles its host at a distance of only 7 million kilometers, which is roughly 5% of the distance between the Earth and the Sun. In our solar system, a planet this close would be a scorched wasteland, stripped of everything including its surface rock. However, because Proxima Centauri is so dim, this tight orbit places Proxima B squarely in the habitable zone. The concept of the habitable zone, often referred to as the Goldilocks zone, is defined by the range of distances from a star where liquid water could theoretically exist on a planet's surface given sufficient atmospheric pressure. It is not too hot and not too cold. When the orbital parameters of Proxima B were calculated, they revealed that the planet receives approximately 65% of the energy from its star that Earth receives from the Sun. This places it well within the theoretical boundaries where water would not instantly boil away into steam or freeze into eternal ice. The mass calculations suggested a rocky composition, a terrestrial world rather than a gas giant, further fueling the comparisons to Earth. For a brief moment in the history of astronomy, the data allowed for the most optimistic of interpretations, suggesting a world of oceans and continents bathed in a perpetual crimson twilight. Speculation regarding the surface conditions became a central focus of scientific discourse immediately following the announcement. Models were run to simulate various atmospheric compositions, ranging from thin, Mars-like envelopes to thick, Venusian blankets. If Proxima B possessed an atmosphere similar to Earth's, the surface temperatures could theoretically hover in a range conducive to biological chemistry. The possibility of liquid water is the primary driver for astrobiological interest because water is the universal solvent necessary for life as we know it. The discovery implied that the ingredients for life might not be rare accidents, but rather cosmic imperatives that arise wherever conditions allow. The public imagination was captured by the idea of standing on the surface of Proxima B, looking up at a red sun looming 3 times larger in the sky than our own sun does from Earth, with the twin stars of Alpha Centauri A and B shining brilliantly as distinct points of light in the distance. This discovery provided a crucial historical anchor for exoplanet research. Before 1995, we did not know for certain if other sun-like stars had planets. In the decades that followed, we found gas giants and super-Earths, but finding a potentially habitable terrestrial world around the very nearest star felt like a statistical miracle. It suggested that such planets are abundant throughout the Milky Way. If the very first star we check has a rocky planet in the habitable zone, the galaxy must be teeming with them. It validated the billions of dollars invested in telescopes and spectrometers and shifted the focus from merely finding planets to characterizing them. Proxima B became the primary target for future observation, the benchmark against which all other nearby exoplanets would be measured, and a beacon of hope that we might one day find a true twin of Earth. The initial euphoria surrounding Proxima B began to dissipate as astronomers turned a more critical eye toward the behavior of its host star. While the geometry of the orbit places the planet in the habitable zone, the concept of habitability is far more complex than simple distance. The primary antagonist in the story of Proxima B is Proxima Centauri itself. Red dwarfs are notoriously active stars, particularly in their youth and middle age, and Proxima Centauri is no exception. Unlike our Sun, which is relatively sedate, Proxima is a flare star. It is prone to violent outbursts of magnetic energy that dwarf anything seen in our own solar system. In March 2017, mere months after the planet's discovery was announced, astronomers using the ALMA observatory witnessed a superflare from the star that increased its brightness by a factor of 1,000 in a matter of seconds. This extreme stellar activity has profound implications for the environment of Proxima B. When a star flares, it does not just emit visible light, it unleashes a torrent of high-energy radiation, including X-rays and ultraviolet light, along with coronal mass ejections of charged particles. Because Proxima B orbits so close to its star, it sits directly in the line of fire. The distance that allows for liquid water also places the planet in a shooting gallery. During a major flare event, the planet is bombarded with radiation levels that could strip away the ozone layer, assuming one ever existed, and bathe the surface in lethal doses of UV radiation. This creates a sterilization effect, where complex molecules are broken down and biological structures are destroyed before they can evolve. The environment on the surface would not be a stable, nurturing cradle, but a chaotic landscape subject to unpredictable and devastating sterilization events. Beyond the flares, the gravitational dynamics of the system introduce another severe complication known as tidal locking. Because Proxima B is so close to its star, the immense gravitational gradient has likely locked the planet's rotation to its orbital period. This means the planet takes the same amount of time to spin on its axis as it does to orbit the star, resulting in one side of the planet perpetually facing the star while the other faces the frozen void of space. There is no day and night cycle as we know it. One hemisphere is locked in eternal, scorching daylight, while the other is trapped in endless, freezing darkness. This dichotomy creates extreme temperature differentials. The day side could be hot enough to boil water, while the night side could be cold enough to freeze the atmosphere itself, causing it to collapse and snow out onto the surface as dry ice. The atmospheric models that once offered hope now highlight the fragility of the planet's potential air supply. A thick atmosphere is required to distribute heat from the day side to the night side to prevent atmospheric collapse. However, the stellar wind from Proxima Centauri poses a constant threat to any atmosphere the planet might try to retain. The pressure of the stellar wind at Proxima B's orbit is thousands of times higher than the solar wind pressure at Earth. Without an incredibly strong planetary magnetic field to deflect this stream of charged particles, the atmosphere would be slowly eroded over billions of years. This process, known as atmospheric stripping, is what turned Mars into a dry desert, and the conditions at Proxima B are far more aggressive. It is entirely possible that Proxima B is a bare rock, a naked core stripped of all gas, baking under the red glare of its volatile parent. Even if the planet managed to hold on to an atmosphere, the radiation environment remains the ultimate hurdle. Studies comparing the X-ray flux of Proxima Centauri to our Sun reveal a terrifying disparity. Despite being dimmer in visible light, Proxima shines brightly in the high-energy spectrum. Over the course of its life, Proxima B has likely been subjected to cumulative high-energy radiation doses hundreds of times greater than Earth. This radiation drives the dissociation of water molecules in the upper atmosphere. When water vapor is hit by UV light, it breaks into hydrogen and oxygen. The light hydrogen escapes into space, while the reactive oxygen is left behind to oxidize the surface rocks. This could lead to a desiccated world where the oceans have long since evaporated and escaped, leaving behind a rusted, dry husk similar to Venus but without the thick clouds. Recent observations have only reinforced this grim picture. The detection of frequent lower-energy flares suggests that the bombardment is continuous rather than episodic. It is not just the massive superflares that pose a threat, but the constant grinding wear of the stellar environment. The habitable zone of a red dwarf is increasingly looking less like a garden and more like a radiation hazard zone. The term habitable zone describes where water can exist, but it says nothing about whether life can survive the assault of the star itself. The reality of Proxima B is a lesson in cosmic context. A planet can be the right size and in the right place, but if it orbits the wrong kind of star, the promise of life may be strangled in the crib. The vision of a second Earth has been replaced by the likelihood of a stressed, extreme world that challenges the limits of biological resilience. The evolving narrative of Proxima B forces a profound re-evaluation of what it means to be habitable. We are learning that the definition of an Earth-like planet cannot simply be a matter of radius and orbital distance. The case of Proxima B challenges the M-dwarf paradox, which posits that while red dwarfs are the most common stars in the galaxy and the easiest places to find rocky planets, they may also be the most hostile to life. This forces astrobiologists to widen their parameters and consider non-traditional forms of habitability. We must move away from the idyllic image of surface forests and open oceans and consider environments that are protected from the stellar fury. If life exists on Proxima B, it is likely not walking on the surface, but hiding beneath it. The search for life in such extreme conditions shifts toward the subsurface and the terminator line. If the planet is tidally locked, the boundary between the day side and the night side, known as the terminator, creates a ring of perpetual twilight. Here, temperatures might be moderate enough to allow for liquid water, provided an atmosphere exists to circulate heat. Furthermore, just as we look for life in the subglacial oceans of Europa and Enceladus in our own solar system, Proxima B might harbor a biosphere deep underground or at the bottom of deep oceans where rock and water provide shielding from high-energy radiation. Life on Proxima B would likely be extremophilic, adapted to utilize infrared light for photosynthesis, or relying on chemosynthesis to derive energy from geological activity rather than sunlight. Future observations are critical to resolving these uncertainties, and the next generation of technology is poised to provide answers. The James Webb Space Telescope, while primarily designed for infrared astronomy, may offer some insights into the atmospheric composition of Proxima B, although the planet's proximity to the star makes direct imaging difficult. The true game-changer will be the upcoming extremely large telescope currently under construction in Chile. With its massive primary mirror, the ELT will have the angular resolution necessary to potentially image Proxima B directly and analyze its light for biosignatures such as oxygen, methane, or the red edge of vegetation. Additionally, ambitious concepts like Breakthrough Starshot aim to send swarms of nanocraft accelerated by lasers to the Alpha Centauri system, providing the first close-up images of the planet, though this technology remains decades away from realization. The study of Proxima B serves as a litmus test for the prevalence of life in the universe. Because red dwarfs make up 75% of all stars, the habitability of worlds like Proxima B dictates the statistical likelihood of extraterrestrial civilizations. If Proxima B is a dead rock, it suggests that the vast majority of planets in the galaxy are sterile, victims of their volatile stars. This would mean that truly habitable worlds like Earth, orbiting stable yellow stars, are rare jewels in a chaotic cosmos. It deepens the mystery of the Fermi paradox. If planets are everywhere, but red dwarf planets are uninhabitable, the amount of real estate available for life drops precipitously. Proxima B teaches us that terrestrial does not mean Earth-like in the ways that matter most for survival. This realization has sobering implications for the future of human expansion. For decades, science fiction has painted Proxima Centauri as the first stepping stone for interstellar colonization. The harsh reality of the radiation environment and the likely lack of a breathable atmosphere suggests that Proxima B is not a sanctuary waiting for us. It is a hostile frontier that would require technology far beyond our current capabilities to settle. It underscores the fragility of our own existence and the unique suitability of our solar system. We are learning that the grass is not necessarily greener on the other side of the interstellar void. The discovery and subsequent analysis of Proxima B is a journey from optimistic fantasy to scientific realism, reminding us that while the galaxy is full of worlds, it may be very short on homes. The term habitable zone is increasingly viewed by astrobiologists as a misnomer that offers false hope to the casual observer. It describes a region of space based solely on thermal equilibrium, a simple calculation of distance and luminosity that suggests where liquid water could theoretically exist on a planetary surface. It does not account for the violently active magnetic fields of the host star, the thickness of a planet's atmosphere, or the geophysical cycles required to recycle carbon and stabilize a climate. In the case of Proxima B, Relying on this thermal definition is akin to suggesting that a person could survive inside a nuclear reactor simply because the ambient temperature is comfortable. The reality of the environment is defined not by the warmth of the star, but by its fury. Proxima Centauri is a flare star, a variable red dwarf that undergoes dramatic increases in brightness and high energy output in a matter of minutes. Unlike our Sun, which has a chaotic but relatively managed magnetic cycle, Proxima is fully convective. This means the plasma within the star circulates from the core to the surface in a continuous turbulent loop, generating magnetic fields that twist, snap, and reconnect with terrifying violence. When these magnetic fields fracture, they release torrents of X-rays and ultraviolet radiation that dwarf anything experienced in our solar system. In March 2017, astronomers observed a flare from Proxima Centauri that was so powerful it increased the star's brightness by a factor of 1,000 within 10 seconds. If a similar event occurred on our Sun, it would likely strip away our ozone layer and fry modern electronics. But on Proxima B, which sits 20 times closer to its star than Earth does to the Sun, the impact is cataclysmic. Such an event does not merely irradiate the surface, it physically erodes the atmosphere. The charged particles slam into the upper layers of the planet's air, imparting enough energy to gas molecules to allow them to escape the planet's gravitational pull. Over billions of years, this process, known as atmospheric sputtering, can strip a world entirely bare, leaving behind a desiccated rock more akin to Mercury than Earth. The question of whether Proxima B has retained any atmosphere at all is the central pivot upon which all speculation about its habitability turns. Without a thick atmosphere to redistribute heat, the planet's tidal locking becomes a death sentence. Tidal locking, the gravitational embrace that keeps one face of the planet permanently turned toward the star and the other frozen in eternal night, creates extreme temperature gradients. On an airless world, the day side would be a scorching desert of baked rock, while the night side would be a cryonic wasteland where temperatures plunge near absolute zero. Any volatile substances such as water or carbon dioxide would freeze out on the dark side, creating a permanent atmospheric collapse. The only thing that can prevent this scenario is a dense, circulating atmosphere capable of transporting heat from the noon meridian to the midnight poles. Climate models suggest that for Proxima B to remain habitable, it would need an atmosphere significantly denser than Earth's, perhaps rich in carbon dioxide, to drive the winds necessary for global heat distribution. Yet the presence of such an atmosphere introduces its own paradoxes. If the atmosphere is too thick, specifically if it retains the primordial hydrogen and helium from its formation, Proxima B might not be a rocky terrestrial world at all, but a mini Neptune. These worlds are suffocated by crushing pressures and soaring temperatures at the surface, where water exists not as a gentle ocean, but as a supercritical fluid, a state of matter that acts like both a gas and a liquid. In this environment, the distinction between ocean and atmosphere blurs, creating a planetary pressure cooker where complex organic chemistry is destroyed as quickly as it forms. We are left with a spectrum of possibilities that ranges from a barren, radiation-blasted rock to a suffocating gas dwarf, with the window for an Earth-like environment narrowing with every new piece of data. The romantic notion of a second Earth is being systematically dismantled by the physics of red dwarf evolution. We must also consider the history of the star itself. Red dwarfs like Proxima Centauri have a prolonged pre-main sequence phase, a youthful period where they are significantly brighter and more luminous than they are in their maturity. For hundreds of millions of years, the infant Proxima would have bathed its orbiting planets in intense heat, potentially driving a runaway greenhouse effect long before the star settled down to its current luminosity. During this epoch, Any oceans that might have formed on Proxima B could have boiled away entirely. As the water vapor rose into the upper atmosphere, it would have been dissociated by ultraviolet light into hydrogen and oxygen. The light hydrogen would escape into space, while the heavier oxygen would remain behind, reacting with the surface rocks to form a crust of oxidized rust. This is the same process that turned Venus into a hellscape, and it is highly probable that Proxima B suffered a similar fate. The discovery of large amounts of oxygen in the planet's spectrum, should we ever manage to detect it, might arguably be a sign of a dead world rather than a living one, a chemical tombstone marking the loss of its oceans. This leads to the profound difficulty of actually seeing what is happening on the surface. Proxima B was discovered using the radial velocity method, which detects the subtle wobble of the star caused by the gravitational tug of the orbiting planet. This method tells us the planet's mass and orbital period, but it tells us nothing about its radius, its density, or its atmospheric composition. Because Proxima B does not transit its star from our vantage point, meaning it does not pass directly in front of Proxima Centauri, we cannot use transit spectroscopy to analyze starlight filtering through its atmosphere. We are effectively blind to its true nature, forced to rely on models and statistical probabilities. Future observatories, like the extremely large ground-based telescopes currently under construction, hope to image the planet directly by blocking out the light of the star. However, the contrast ratio between the star and the planet is immense, and the angular separation is minuscule. It is like trying to spot a firefly hovering next to a searchlight from thousands of miles away. Even if we were to detect biosignatures, the interpretation of those signals would be fraught with ambiguity. The unique radiation environment of a red dwarf can produce false positives that mimic the signs of life. For instance, strong UV radiation can break down carbon dioxide and water vapor to produce oxygen and ozone, the very gases we associate with biological activity. A planet could be completely sterile, and yet appear, through the lens of a telescope, to be teeming with life. This danger of misinterpretation forces scientists to be incredibly conservative. The standard for confirming life on Proxima B will not be the detection of a single gas, but the identification of a disequilibrium in the atmosphere, a cocktail of gases like methane and oxygen that should not coexist without a biological source constantly replenishing them. But on a tidally locked world with unknown geological activity, even these combinations could potentially be explained by exotic volcanism or atmospheric photochemistry. The narrative of Proxima B is also a story about the architecture of our galaxy. Red dwarfs are the most common stars in the Milky Way, making up about 75% of the stellar population. If planets like Proxima B are standard for these stars, and if these planets are routinely stripped of their atmospheres and sterilized by flares, it suggests that the vast majority of real estate in the galaxy is uninhabitable. This hypothesis, often called the red dwarf filter, offers a chilling solution to the Fermi paradox. We see no aliens because the most common type of solar system is a trap, luring planets into the habitable zone only to bombard them with lethal radiation. Under this framework, the silence of the universe is not a sign of emptiness, but a sign of the extreme rarity of stable stars, like our Sun. Yellow dwarfs, with their steady light and manageable magnetic cycles, may be the only true cradles of civilization, making our existence far more precarious and solitary than we previously believed. There is, however, a glimmer of alternative speculation that keeps the scientific inquiry alive. Some models propose that if Proxima B formed further out in the system, beyond the snow line, where volatile compounds freeze into solid ice and then migrated inward, it could have arrived in the habitable zone with a massive inventory of water. If the planet is an ocean world, With a global sea hundreds of kilometers deep, the water itself could act as a shield. A deep enough ocean could protect the lower layers from high-energy radiation, potentially allowing life to exist in the abyssal depths, clustered around hydrothermal vents, completely cut off from the violent sky above. In this scenario, the surface would still be hostile, but the interior could be a sanctuary. Yet, an ocean world brings its own challenges. Without a silicate cycle to regulate carbon, essential nutrients like phosphorus might be locked away in high-pressure ices at the bottom of the sea, starving any potential biosphere of the building blocks it needs to grow. The sheer variability of the environment on Proxima B challenges our definitions of adaptability. Life on Earth has survived ice ages, asteroid impacts, and supervolcanoes, but it has never had to contend with a sun that changes its output by orders of magnitude in minutes. Any organism evolving on the surface of Proxima B would need biological mechanisms that are almost inconceivable to us. They might require rapid response pigmentation to shield themselves from sudden UV spikes, or perhaps they would be amphibious, retreating beneath the surface during flare events. The plants, if they existed, would not be green. To absorb the dim infrared light of the red dwarf, photosynthetic life would likely be black or deep purple, evolved to scavenge every available photon. The ecology of such a world would be dictated by the rhythm of the flares, a biology of constant crisis management, where survival depends on the ability to endure sudden ionizing violence. We must also look beyond the planet itself, to the system it inhabits. Recent observations have hinted at the presence of dust belts and potentially other planetary companions, such as Proxima C, a colder world orbiting further out. The presence of dust belts is significant because it implies a history of collisions and grinding, the messy leftovers of planetary formation. These belts are the debris fields of the system, and their structure can tell us about the dynamic history of Proxima B. If the system has been dynamically unstable, Proxima B might have been subjected to heavy bombardment by comets and asteroids. While large impacts can be extinction-level events, they are also the delivery trucks of the cosmos, bringing water and organic compounds to dry worlds. It is a delicate balance, too few impacts, and the planet remains dry too many, and the crust is pulverized and molten. The architecture of the Proxima system appears to be complex, suggesting a chaotic past that has shaped the conditions we see today. The dream of visiting Proxima B, of crossing the 4-light-year gulf to see it with our own eyes, drives projects like Breakthrough Starshot. The concept involves sending a fleet of tiny gram-scale probes propelled by powerful ground-based lasers to 20% the speed of light. Even at this blistering speed, the journey would take 20 years, followed by another 4 years for the data to stream back to Earth. The engineering challenges are staggering, from keeping the laser beam focused over millions of kilometers to protecting the tiny probes from interstellar dust impacts that would hit with the force of a bullet. But the scientific payoff would be the resolution of the red dwarf mystery. A flyby mission could take pictures of the surface, measure the magnetic field, and taste the exosphere. It would definitively answer whether Proxima B is a rocky corpse or a struggling oasis. Until then, we are like cartographers mapping a continent we can only see through the distortion of a heat haze. The psychological impact of Proxima B's discovery cannot be overstated. For generations, we looked at the stars and wondered if there were other Earths. Finding one right next door, astronomically speaking, felt like destiny. But the subsequent realization that next door is a radiation-flooded trap serves as a maturity test for our species. It forces us to abandon the golden age sci-fi optimism that portrayed the universe as a collection of waiting paradises. It pushes us toward a more rugged, utilitarian view of space exploration. If we are to expand beyond the solar system, we will not be landing in lush, oxygen-rich forests. We will be building pressurized habitats, digging into regolith to shield against flares, and manufacturing our own air. Proxima B teaches us that the universe does not owe us a living. It provides matter and energy. But the comfort and safety of a biosphere are rare and fragile achievements that we may have to engineer for ourselves. Furthermore, the interaction between Proxima B and its star highlights the importance of magnetospheres. Earth's magnetic field is our silent guardian, deflecting the solar wind and preserving our atmosphere. We do not yet know if Proxima B generates a magnetic field. Tidal locking can slow a planet's rotation, and since planetary magnetic fields are often generated by the dynamo effect of a spinning molten core, a slow rotation might result in a weak or non-existent field. Without this shield, the solar wind of Proxima Centauri, which is much denser and more forceful than our Sun's, would have direct access to the atmosphere. This solar wind pressure can push the magnetopause, the boundary where the planet's magnetic field meets the stars, all the way down to the surface. In such a scenario, the surface of Proxima B would be constantly bathed in stellar plasma, a condition that would likely sterilize the crust and prevent the formation of complex molecules. The study of Proxima B also forces us to refine our understanding of super-Earths. Proxima B is slightly more massive than Earth, classified as a super-Earth, a type of planet that has no analog in our own solar system. We do not know if super-Earths have plate tectonics, a crucial cycle for regulating planetary temperature. On Earth, plate tectonics recycle carbon dioxide, pulling it down into the mantle and releasing it through volcanoes, acting as a thermostat over millions of years. A planet with higher gravity might have a stiffer mantle and a locked crust, preventing this cycle from operating. If Proxima B is a stagnant lid planet, meaning it has a single immobile crustal plate, it might be unable to recover from climate extremes. It could be stuck in a permanent snowball state or a permanent hothouse, lacking the geological flexibility to self-correct. The mass of the planet therefore contributes to the uncertainty of its habitability just as much as the radiation from its star. As we continue to monitor Proxima Centauri, we are essentially watching a weather report from hell. The flares are not just bright. They are spectral shapeshifters. During a flare, the star's light shifts dramatically toward the blue and ultraviolet. This sudden change in the quality of light would wreak havoc on any biological circadian rhythms or photosynthetic processes adapted to the star's usual red glow. Imagine a plant on Earth that relies on steady yellow sunlight suddenly being blasted by a blue-white arc welder for 10 minutes, followed by a return to normal. The biological stress of such variability is difficult to model. It suggests that if life exists, it must be subterranean or aquatic, using the rock or water as a buffer against the capricious temper of the star. The surface is likely a no-man's land, a place of sterilization and erosion. This brings us back to the concept of the terminator zone. If the day side is too hot and the night side is too cold, the only habitable real estate might be the thin strip of twilight between the two, known as the terminator. Here, the sun would sit forever on the horizon, casting long, freezing shadows. The temperatures might be mild enough for liquid water, creating a ring ocean that circles the planet. But the winds in this zone would be ferocious. The temperature difference between the day and night sides would drive a constant roaring gale across the terminator, a global storm that never ends. Living in the terminator would mean existing in a perpetual hurricane, under a sky that never changes. It is a niche, a precarious foothold, but it represents the most optimistic scenario for surface life on Proxima B. Even here, the radiation would penetrate, but the geometry of the planet might offer some respite if the atmosphere is thick enough to scatter the incoming particles. The investigation of Proxima B is a masterclass in the limits of remote sensing. We are trying to deduce the biology of a world based on the physics of its star and the mechanics of its orbit. It is a detective story where the clues are photons and the crime scene is 4 light-years away. Every study that comes out oscillates between hope and despair. One paper simulates a dynamic ocean. The next proves the atmosphere should have vanished 1 billion years ago. This oscillation is the scientific method in real time, a struggle to constrain the variables of a chaotic system. It reminds us that truth in astrophysics is rarely binary. Proxima B is likely not simply dead or alive in the way we understand it. It may be a world of complex prebiotic chemistry that never quite makes the jump to life, or a world of simple slime that never evolves into complexity because the environment constantly hits the reset button. Ultimately, Proxima B serves as a mirror. By studying its hostility, we see the specific fortuitous circumstances that allow Earth to thrive. We appreciate the stability of our yellow dwarf star, the protective embrace of our magnetic field, and the perfect distance that keeps our oceans liquid. Proxima B is a warning against taking the Earth-like label literally. It is a rocky world, yes, and it is in the habitable zone, yes. But it is a world shaped by a different set of cosmic rules, governed by a star that is both a creator and a destroyer. The dark truth about our closest neighbor is that it is likely a desolate monument to the violence of the universe, a place where the conditions for life are dismantled as fast as they are assembled. It is a destination that challenges our technology and our philosophy, forcing us to accept that in the grand casino of galaxy formation, Earth may have hit a jackpot that is not easily repeated. The journey of understanding Proxima B is far from over. New telescopes will soon turn their gaze toward Alpha Centauri, peeling back the layers of glare to hunt for the faint thermal glow of the planet. We will look for the spectral fingerprints of water, methane, and carbon dioxide. We will listen for radio emissions that might hint at a magnetic field. But as we gather this data, we must remain steeled against the likelihood of disappointment. The universe is under no obligation to be hospitable. Proxima B may well be the first of many worlds that teaches us a hard lesson. That being a planet is easy, but being a home is a miracle. The silence radiating from the Proxima system is heavy with implication, suggesting that while the path to the stars is open, the destination might be nothing more than a graveyard of potential, a rocky tomb orbiting a red eye that never blinks. This is the reality of our cosmic neighborhood, crowded with worlds yet profoundly, terrifyingly lonely.